All right, guys. So oh, wait. Are we recording? Yeah. Let me. All right, we're recording. All right, so I am recording. You guys are section one on Wednesdays, Mondays and Wednesdays. Again, we're on week 4, and exam 1 is in 2 weeks from today. So we've covered all these modules so far. We've looked at one algorithm from scratch, KNN, but we've also covered k-means as far as using it, right? And that covers unsupervised learning. So we saw that last week. I'm not going to give an assignment for this one. Instead, today we're going to continue with our discussion of SKLEARN, essentially, right? So that's one tool that you should definitely know about for machine learning. It's somewhere between Weka and building something from scratch, right? So sklearn is, well, you've seen me use it already. You saw me use it with the k-means algorithm on Monday, essentially, right? So I did that for unsupervised learning. So you should know about these techniques. These can be deployed, so you can build, and you will have an assignment. I'm still working on it. Where you will deploy, well, you'll deploy twice with Onyx and also with something called Fast API. But in the next couple of weeks, I'll have that complete and I'll give you that assignment. And it'll be like one or two of these algorithms that you have to deploy, right? It's a client server type of architecture. So that's when you want to, you know how we run the code and get results. So whenever you need to do that for whatever reason, right, you can run you can have like your own API essentially. All right. So yeah, today I'm going to click on, so you can see the title is SKLearn ML models. So we're going to look at several other machine learning algorithms. Some of these we will discuss and build them from scratch later on, like the multi-layer perceptron. So as I said, we're currently on week 4. I usually like to have like 3/3 of the course. The second third will be neural networks, that starting from the perceptron and so on. So there's a lot of history there. I'll talk a little bit about history today as well with these algorithms. We're still not covering like neural networks. The only one that we've used in Weka and we'll use today is the multi-layer perceptron. But later on, it'll become very clear how those work. And then next week probably I'll cover naive Bayes, which you've seen me used already in Weka. So we're gonna build that one from scratch. So that's another one, non-neural network one, a probabilistic one. And then we have to cover performance metrics, and like I said, singular value decomposition. Likely the perceptron will happen after exam 1 with the whole sequence of hot-field networks, which somebody won a Nobel Prize for this one, the perceptron, and there it is, MLP, and so on, right? And then that gets us into PyTorch also, and so on. But we'll build some of these from scratch with NumPy, etc. All right, and then the homework, I'm still working on that. All right, so yeah, so the plan today should be pretty easy. There will be a very small homework assignment for this one. As you might imagine, the same idea, find a data set, use several of these techniques, and provide performance metrics. As you can see, I've said this many times, when we started the first couple of weeks, it seemed like so many things were new, but it starts to get repetitive, right? The pipeline is usually the same, some data, we process it, some algorithm, we get performance metrics, okay? And the key is in figuring out how to go from raw data to that specific format that we want to use. So I put together some of these here. So I'm going to click on code. And I have several things in here that we can use, several algorithms, or a few concepts with sklearn. sklearn is very powerful. It's definitely a tool that you can use to solve like real problems. It's just not going to be something where you're using massive amounts of data. So if you're using massive amounts of images, text, things like that, obviously we're going to look at techniques for those. But for many of you, if you work in a company that makes wine, or company that makes whatever widgets, like Industrial, Gary Works, US Steel, something like that, right? The data sets are actually not going to be massive. They're going to be, finance, right? So even in finance, right, the data is not going to be massive. And so a lot of these algorithms are very helpful, get you going really quickly. All right, so usually this first third of the semester is kind of focused on that. All right, so as you can see, a lot of these scripts, clustering we've already talked about. We did singular value decomposition, which is like PCA, and we can look at this as time permits. Bag of words approach, we already covered that on Monday. So today we're just going to focus on this one, SKLEARN, several algorithms. I'm going to use, once again, Colab. Remember, most of what we're going to be using is Colab. And we're coding. Weka was just really to give you the pipeline. It's still a tool that you can always use, right? But, we'll have it as an additional tool, but it's not going to be the main focus. All right, so by now you should understand the pipeline. We have some libraries. We need to bring in the data, process the data. We have a performance metrics function, and then we have a few algorithms, right? So we've seen an example of how to implement KNN from scratch. Now today we're just going to use, the built-in object from SKLearn, from SKLearn to do k-nearest neighbors. Okay, so I'll just show you the workflow once again. So that's what we can call these things. So SKLearn has their own workflow kind of thing that, to get used to doing. So today that's the focus, and then I'll assign some kind of a homework assignment, find a data set, and write a report essentially. All right, so let's go ahead and start Colab. It's in your notebook. Okay, I'm going to add a few code segments here. All right. Hello, how are you? So we're going to bring in the libraries, essentially. So, a few more libraries. But a lot of these, again, they get repetitive. So you can see, I'm going to run this SKLearn data sets. I'm still, sometimes I can read the data from like my CSV file. We already know how to do that in Pandas. It's the preferred approach. You know how, if you have strings, etc., you convert them into numbers. NumPy, it's a tool that we can use. Our train test split, which we'll be using throughout. Standard scalar, the metrics here, matplotlib, pandas, as you can see, and sklearn decomposition. So today we might play with that idea again of PCA or SVD, but I think I've covered it already, and hopefully that was clear in the Monday lecture when we talked about compressing the number of dimensions in a vector space. So that's a key concept that you must master. All right, so that's done. If you want to print all the values in a NumPy array when we look at it, we can set the parameter to the print option. Do that. So now the data set that I'm going to start with is just the iris data set to keep things simple. Okay. Then we might link it to some other data set. But yeah, same idea, right? So let's take a look at this. Let's once again print out the shapes. So x.shape. So I only have 3 columns for whatever reason. Let me actually take a look at this. Here. Okay, that looks better. Okay, and then I should have the y targets as well. So now we can print the shapes. X dot shape 150, 4. All right. So the same function, print the metrics, right? So we, as I've said to you before, we haven't looked at the calculations of this just yet. You know, we'll probably start that at the end of the lecture today. Just go over some of those ideas and how they work to kind of give you that intuition. But yeah, it's essentially, remember, provide the algorithm. We provide a list of the predicted values and then a list of the real values. And then we do some kind of comparison, precision, recall, F measure, and the confusion matrix. Okay, so that's the function. All right, and now essentially we split the data. So same idea as before. We take our X and our Y, we do a train test split, maybe on 20% split. Okay, so that gives us, for instance, X train dot shape, and there you have it. So it's 30, 4, right? So we confirm that we have that available. All right. Now here, I'm going to use like this strategy. Essentially, I'm going to create several functions for these algorithms, and these algorithms, each of these functions is invoking the specific algorithm from SKLEARN. So some of the functions that we can look at, for instance, are the multi-layer perceptron, which is a neural network, the same neural network that we had in Weka, essentially the same like architecture. I'll comment it out. We also have KNN, and you can see also, by the way, I provide to it like X train, Y train, X test, Y test. So I can provide this information, so I can do the training in there, but I can also evaluate the predictions, print the results. Okay. So you can see here I can create a KNN, I can create a random forest, decision trees, an SVM, support vector machines, which is a very interesting algorithm, and something called logistic regression, which we will actually look at later. So of some of these, we've already looked at this one as far as how it works. We'll look at multi-layer perceptron, logistic regression, trees, and SVM, and the algorithm essentially later. But yeah, so here, just giving you a basic like pipeline of how we do this. So now we need to define these functions. So I'll just pick one. I'll take KNN, for instance. And really take this for now, or actually let's take something. Okay, so you can see this is, so essentially what we're covering here is the overall workflow of SKLEARN. Okay, so essentially SKLEARN is going to take the X train, Y train, X test, Y test data that I'm providing. I'm going to invoke then from SKLEARN, so you can see that here, from sklearn.neighbors, and I'm going to invoke the K-neighbors classifier. That's it. So that's, that imports the object. So, unless I specify, you can, unless I say, please use the raw KNN implementation, you can always just use this and that should be fine. All right. You can always also benchmark your algorithm to this, etc. So you can see here, now that we have the module, we can instantiate a KNN object. It's a K-neighbors classifier. We specify the number of neighbors as 5. We've used 3 in the past, so usually a uneven number, right? Some kind of a metric, Minkowski. There are other metrics beyond the Euclidean distance, and that's there's something called the Manhattan distance and so on. So those other types of distances might actually give you a slight advantage every now and then. You guys see that? So it's just a replacement for the Euclidean distance. Then after that, notice the workflow is pretty simple. SKLEARN has these ideas of KNN dot fit. So then you do X train, Y train, right? And then once something is trained, then you do the evaluation. So you do KNN predict on the X test data set. Do you guys see that? Any questions? So pretty easy. I think this is, pretty straightforward. And that produces the Y pred. So just the predictions given your data. So you don't have to do all those steps. It just does it for you. And then after that, if you notice, we just print stats percentage train test, the same function that we had used before, and evaluate the performance. How simple is that? All right, so that's SKLearn is, and again, we'll look at it today, just something you should be familiar with, but is very helpful. SKLearn is a very powerful library. So now if you notice, I'm going to run KNN here. I think I've run all the other cells, so I did the split. And let's see the performance. So I run it, and there you go. So as you guys can see, well, this is the iris data set, of course, but it performs really well. All right, all the values are on the diagonal. There are a few misclassifications, actually. And we have an accuracy of 0.97, a precision of 0.96, and F measure of 0.96. Any questions, guys? So pretty straightforward. All right, so this, remember, is a vector space type of an algorithm, but we can try others. So now the idea is so I did KNN. Now I can, for instance, grab a decision tree. Right, so if you remember, Weka provided this as well, but now we have the advantage that this is more something that you can deploy more, you got more control of it, etc. So let's add this function here. The flow is very similar. You just sometimes have to change a few of the parameters, right? That define some of these. But you can just use the full parameters. So in this case, we're going to do the decision tree. So X train, Y train, X test, Y test. So I'm going to comment out KNN, and instead I'm going to uncomment decision trees, as you can see here. And now let's look at the workflow. So you can see from, so we have our X train, Y train, X test, Y test. From sklearn.tree, we import the decision tree classifier. Okay, the decision tree classifier, some parameters here. So it's got something called criterion, right? Max depth. So criterion is entropy, right? The underlying metric. Max depth has to do with the fact that you are creating a tree, right? So it's the depth of the tree, like you create a node and then another node and how deep it's allowed to go. Okay? Random state, so on. Then once you've instantiated the tree, you can go ahead and fit it on the data. So you just do X train, Y train, you fit the tree, okay? And once you fit the tree, the model essentially, which remember it's not a neural network model, but a different kind of a algorithm, you can now predict on the X test data. This once again gives you your Y pred. What do? You take your Y pred and your Y test and you run performance metrics on it. Okay, so let's go ahead and try this one. And you can see I have a few other functions in here for visualization, things like that. But I'm leaving them commented out for now. So so that ran. And now let's try to run the decision tree and see what we get. And perhaps we want to leave this result so that we can compare. So instead, let me just move it down to here. And as you can see, that's my performance. So obviously, I'm using the same data set, right? Same randomization, same split. And so far, the KNN performed the best. Do you guys see that? Remember that the metric, if you can only look at one metric, you should look at F measure. F1 measure is the key. If you can only look at one metric. But today, as time permits, we'll start diving into the meaning of these metrics, precision, recall, and so on. And I have two examples. All right, so as you can see, there were more misclassifications this time around. There were 5 misclassifications here, as it seems. So, yeah, that's an issue. Any questions on this one? So far, both of these algorithms are completely different from neural networks, right? So that's one of the things that you should get out of this. Neural networks are the current state of the art, right? And so we'll spend at least 4 or 5 weeks on them coming up. But you should be aware that there are other techniques like the vector space based, distance metric based, the trees, which are really important. And as I've said, there is a tool, although I don't have it in this example, called XGBoost. That's like the super trees algorithm. All right. So we'll cover a little bit of that. All right. Let's try another one. So let's try the multi-layer perceptron. So this is the neural network one. So before the explosion and everything with neural networks, this was pretty much the neural network, model that everyone used. So I can pretty much say, because I lived through that time, right, that before like 2012, this was it when somebody said neural networks, right? So, but yeah. Called, and we'll understand what a perceptron is and what is this multi-layer later. All right, and the history is actually pretty interesting. All right, so in this one, this is the multi-layer perceptron, and actually, let me move this up. All right, multi-layer perceptron. So as you can see, the workflow for SKLEARN pretty much the same: X train, Y train, X test, Y test. Here you can see I invoke from sklearn.neural network. I import an MLP classifier. So you can see here, I can specify some aspects of the neural network. Okay. So MLP classifier, so you use this solver. This is like the optimization. Some parameters. And then it's got this is like your first look at what a neural network is. So we'll look at this in detail, but essentially you're defining the architecture of this neural network. So 20 means one hidden layer with 20 neurons. 2020 would mean 2 hidden layers with 20 neurons each. So that's what we have here. So this is, like a deeper neural network. Keep in mind, with our implementation, with our CPU, these take longer to train. Okay, so that's a key concept to realize. But since we're here, I forgot about this part, and I did not connect my. This is, this thing that I'm about to do, we'll do a lot by the end of the semester when we focus on neural networks, but it's key to know. All right, so let's continue with this idea. All right, so I have 2020 hidden layer size. Um, so let's go to the whiteboard. It's whiteboard classic. Okay, perfect. So it's working. All right, so it says that it's got 22 hidden layers of 20, right? So a neural network, you guys, we all know about the brain. We know what a neuron is. It's like a thing, right? A little thing in our brain, and it's connected to another one, right? And then that one is connected to another one. So essentially, you have billions of those all connected. And so it's like in the brain, you have like a little thing and called neurons, right? This is the idea, the intuition, and then there's connection. And these have names like dendrites or something like that. Well, the key to understand this is that, think of this as a function where it takes in a value and it produces something else. Do you see that? So essentially, it's one way of thinking about it. So like a value comes in that depending on what's in here, that might become a 1 or a -1. Do you see that? And then that goes sort of forward, right? So think of it almost as electricity, right, that goes forward. And now this connection will do something to that value. So let's say that this value is 1, so it goes forward, but then here this connection also has a meaning which could be another value. So then once I take this one times this one, it just becomes 0.5. Do you see that? And that goes into this neuron, which might be a function as well with 0.5, right? And then what happens? That produces a value. Let's say for some reason 2. And then this one is 0.10, so that now this comes out over here like 0.2 and so on. Do you see that? So that's essentially, like mathematically, that's kind of what's happening. But the brain is a little bit like that, okay? So it's all these connections, all right? So now, and some architectures, as we will see, with hot field networks are not exactly like going in one direction. They'll go in like all kinds of directions. But the neural networks usually go in just one direction, all right? So whenever we refer to them, we'll have a way of representing them mathematically later on, and it'll become straightforward. Without a doubt, we'll look at iris again and kind of get an intuition. But whenever we draw an architecture for a neural network, we'll usually say that it's got an input layer, hidden layers, at least one hidden layer, and then output layers, okay? So in this example, what is the data set that we're looking at? It's the iris data set, correct? Right? So iris has how many features? 4, right? Petal length, petal width, sepal length, sepal width. Do you guys see that? So essentially, every vector in that matrix is 150 by 4, right? And where these are the features, F1, F2, F3, F4. So essentially, when you talk about the input layer of a neural network, guess what? It's got 4. Okay, that's it. It's set in stone. It depends on the data. Then what's happening is these values are connected to a sequence, to another layer, right? Another layer of neurons. And so the information from here goes times some weights to produce the next set of values here. Okay? And then, so now the example says, if you remember, that there's 2 hidden layers with ... 20 neurons each. ... Do you see that? So now I know the dimensions of this. I know the dimensions of this. Do you guys see that? So essentially, those numbers have meaning. Again, we'll look at the mathematical representation of this later on. It's actually a very simple thing that you guys, it should be easy to understand. And you're doing the tensor operations already. That will also help you with that. And once you're at the last layer, then you produce an output. So these are called hidden layers, hidden 1, hidden 2. And the final one, output, will have the classes, right? So how many classes do we have in iris, in the iris data set? The species, right? So there was Setosa, virginica, and versicolor. There's 3. So you would represent the last vector as 3 neurons. So the probability that it is, let's say 0.96, and this is 0.02, and this is 0.02. So essentially it's saying that the probability that it is the second class is 0.96. Do you guys see that? And so that's kind of the intuition for now. We're going to leave it there just as a quick introduction to give you some context as to where that 20 by 20 is coming. The tensor operations that you're doing will help you to develop the mechanics for it, and then in about 2 weeks we'll dive into neural networks and start creating them from scratch in NumPy. All right, so that should be fun. All right, so yeah, so we covered that. So now we can go back to the SKLEARN example code, and you can see that this is meant to make your life very easy, right? So you just built the architecture. Keep in mind that as you make these deeper, more neurons, it takes longer to train them, right? So this thing is very iterative. It's like you give it data, it goes forward, predicts, calculates an error, back propagates, updates something, and then it just keeps doing that over and over and over and over. And so the more layers you have, the more calculations it has to do. And that's why we have to at some point scale up to GPUs, all right? Because what we want to do is not one operation, right, per second, but 64 operations in that same second. And only GPUs can do that. So we'll cover that also later in the semester. All right, and so yeah, so we instantiated a neural network. Keep in mind, if you have 2 hidden layers, technically, you start to get into deep learning. If you've ever heard of the term neural networks versus deep learning just means a neural network with more layers. That's it. So if I say 3 layers, I mean I'm getting into deep learning territory. Do you guys see that? So that's essentially what it is. But what's interesting is that in the 90s, they just didn't have the computing power to train these models or the data. If you had 1 million of these samples, training something like this was really difficult with that technology back then. This is why for AI, as it continues to grow, you hear all this about data centers, right? So I'm sure all of you have heard data centers this, data centers that, and it's just because it just requires so much computing to train these models because they just keep getting even bigger and bigger and bigger. Hopefully there will be a breakthrough at some point that says, no, actually, we can do it this way, and then they're tiny, right? So that would be. I mean, our brains are not, are small, right? So and we're able to do a lot of things. So there may be still some secrets out there, but anyway, so we have the classifier here, and the basic workflow is to use the object, the classifier, you fit it on the training data, so X train, Y train, right? And then once again, we're going to predict on the X test data and print out the results. So let's do that. So I've created the function. Now let's grab the multi-layer perceptron. All right. So we grab the multi-layer perceptron, and guess what? Ah, wow. So there we go. Here's an example of neural networks actually beating everything else, right? So we had KNN at 96.7. We had decision trees at 93, but if you look, now we have the multi-layer perceptron with 2 hidden layers at 98. So that extra architecture, etc., may have helped out. And notice we only had 2 misclassifications. Any questions? Does this make sense? All right, so yeah, so this is a neural network one. Let's take a look over here. So we covered, so the next one I want to try out is the SVM one. I have this in another. KNN, logistic regression. SVM, here it is. All right, so let's grab SVM. All right, so this is called a support vector machines. Okay, support vector machines. This was a very interesting algorithm just before deep learning. It is not a neural network, right? It is a different kind of algorithm, but it actually follows this idea, our theme this week of a vector space model. Okay, so let's talk a little bit about it. Let's go to the whiteboard. So let's talk about SVM, support vector machines, SVM. So around 2010, 2011, this was the most popular machine learning algorithm in data science, more so than any neural network. Okay, this was the most promising, the most important. So the issue is that people, neural networks have been around for since the 40s. People, there's been all these like AI booms, and then there's an AI winter. For me, this is why I'm a little bit concerned currently, right? Like we've been definitely on an AI boom for a while since 2012, and it just keeps growing, and this time is probably different, hopefully. But from experience, there's been all these busts of AI. There's all this hype, and then all of a sudden, stock market crashes, something like that related to those companies, and people hate AI for like 10 years. And that's called an AI winter. This has happened many times. This time seems to be different, but who knows? Anyway, so there had been an AI sort of boom. No, yeah, an AI boom in the 80s, early 80s, then there's a bust again. And so the reason is neural networks are great, but then in the 90s, people, sometimes people treat them as a black box. So they're difficult to interpret. The math is not as like clear, etc. So what people like is these things called linear models. They like to create a model where you have this. This is the perfect thing for people in data science. Let's say here we have two classes, right, of data. They want a model that is just a straight line. This is what the holy grail, right? And you guys understand that if we scale this to 3 dimensions, right, instead of a line, what do we have in 3D to separate the data? A plane, right? You can see that obviously. Like here, if I want to separate points down here from here, I draw a line, right? But in this room, if I want to separate that group from that group, I can't just draw like one line necessarily. I draw a plane between the two groups, right? So, and that scales up. If I have 20 dimensions, there's a hyperplane or something like that. So the same idea as the Euclidean distance. So all this scales. So solving a function like this that separates the data perfectly is easy. It's easier, mathematically well-founded. But the problem is sometimes the data is difficult. We'll do this example. It's called the XOR problem, right? And how neural networks solve this. Sometimes the data will be like this. Do you guys see the problem? You can't have a line that separates this data, right? You need some kind of a curve. So fitting that kind of a line is harder to do. What about the problem where you have something like this? Right? So that's a circle that separates the two classes. Do you see that geometrically and this idea of geometric things? Neural networks can definitely do this. They simulate creating these functions, right, that allow you to separate the data. But people they are an alternative to use. But people after one of those AI winters, just didn't want to use them. They questioned whether they had capacity, all that stuff, right? And so they were looking for other alternatives. And so this idea of support vector machines was invented, which is really interesting. And keep in mind, what they want is to be able to separate the data with a line, a plane, or a hyperplane, okay? So that's the key idea. So what they came up with support vector machines, it's a trick to take the data and project it to a higher dimensional space. Do you see how on Monday, our discussion was what? We had, the data, right? We had the sentences. If you remember sentence 1, sentence 2, and we had, all the words, cat, dog, dot, 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 and we had maybe about 20 features, right? And what did we do? We used singular value decomposition, and we compressed the space. Do you remember that? So we went from, let's say, a space that is R20 to a space that is, what was it? R2, right? For plotting, and that still worked. Do you guys remember that? So we did that. Well, support vector machines does almost the exact same trick, but in an opposite direction. Now support vector machine says, okay, I'm in R20, but in R20, I cannot fit a simple model that separates the data, which is like the easiest thing that I can do, right? Because its data looks like this or it looks like that, so I need something like a neural network, very complicated stuff to actually build a classifier that works. So then some brilliant people had this idea, okay, well, let's just reverse the idea of PCA or SVD, and instead of compressing the space, let's expand it somehow. Let's find some other space, right, where we can represent the data. So now they're saying, and you don't even know what that space is. You can just go from R to, it could be R1000, 1,000 dimensions, right? And so so remember, every point in the R20 space is projected now to this other space called, that's bigger. And what's the goal then? The goal is that there's an algorithm, obviously, there's like a technique, and now every point is mapped to this new higher dimensional space where you can now, with a simple model, separate the data and build an effective classifier. Do you guys see that? So let me give you an example of this. So imagine I have that idea, right? I have that idea of this is called the XOR problem. It's a very famous problem. The XOR as in, you guys, like that logic of XORing, right? So, sorry. Okay. So this is the XOR problem. All right, so here, there's no way, you guys agree, that I can use a line. There is no line or a plane or a hyperplane that will, go perfectly divide this data, right? There's going to be misclassification. The only thing I can do is, create a function that does something like this, right? And you can create these with neural networks and other algorithms, decision trees, they approximate this behavior. But people didn't want to use fancy algorithms. They want to use like the simplest one, the one that only builds planes, hyperplanes, or lines. So what trick do they use? Well, now here's the trick. So let me change to red again. Okay. So remember, this is currently R2, a two-dimensional space, right? There's nothing I can do because all the points live only in this space. I can't move them. I mean, I can stretch it maybe or something like that, but it doesn't work. So what do? I add a dimension. Do you see that? Here, this is two-dimensional, I added a third axis, I just effectively expanded the space into a three-dimensional space. So here's I'm adding this one. Support vector machines, the algorithm does that. It expands the space. And now that I have more room in the space, it explores through the algorithm ways that the data, so I'll change color here, is moved. So you see all the circles here. You guys see what I'm doing? I'm moving all these circles, like I'm grabbing them from the hole and just moving them. So I'm moving them here. So see that? So essentially, they're no longer in there, right? Remember, those circles are nothing more than points in that vector space. Do you see the trick? And this is what the algorithm does. And then once I've done that, it's very easy to just train a very simple, oops, sorry. It's very easy to train. Imagine this is a plane that separates them perfectly. Do you see that? So that's essentially the idea with support vector machines. This is not neural network based at all. This is just geometrical, right? So we project all the points into a higher dimensional space through something called the kernel trick. And we figure out, and we do it in such a way that the performance goes up, right? So it's almost like, think of it as you're trying multiple spaces, you're projecting into that space, you build a line, measure performance, and guess what? It's really bad. So what does that tell you? That's a bad space. Try another one. So you try another one, you project to that space, and you keep doing that, and that's a simple intuition to understand this idea, okay? So that is support vector machines. It also had another trick, which was that actually it created three lines. So it created a third line. See that? So there was like a central line, and there were two lines on each side of that central line. Those were the margins. That's where the name support vector machines comes in. So essentially, it's almost like there was a separation, right? Let's say that I build a separation between you guys and you guys, but I'm like, instead of just being a rope or something, it's like I put in a cardboard, right? So like this. And so I'm just separating even more and making sure that the classification is better. All right, so far with this one, I'm only giving you the intuition of support vector machines. We might look at implementing this later in the semester, but this is yet another one that is not neural network based. And like I said, I mean, these things, you never know. These things could come back, right? So it's interesting how it happens. A super support vector machines comes in and it just like blows everything. And it becomes the most important algorithm. So neural networks were like that. They were amazing, then they were awful, then they were amazing again, then people hated them. There was this huge winter. People did not want to be associated with neural networks. I don't know if you guys know who Jeffrey Hinton is, but he is considered the godfather of AI. And when he would go to conferences during this era, he'd get like the worst table. Nobody wanted to be associated with them. They made fun of them. But, that also there's a lesson there about persistence, right? He just really liked what he was doing, and it turns out he changed the world. So anyway, but I can tell you because I spent years studying this thing. And at the end, I've never used it since then. So these are important lessons about how these algorithms, evolve. Today, the focus of this course, you know, 1/3 of the class will be neural networks. That could change in 10 years, and you know, it's something else. Or anyway, all right. So that's support vector machines. So let's switch back to the implementation. All right, let's take a look at the workflow here. It always performed really well. For some problems, it was really great. So we have our X-train, Y-train, X-test, Y-test. From SKLEARN.svm, we import SVC. Notice here, there's a few parameters that you always specify for support vector machines. So you can see I have them here. But there's something called the kernel. That's that projection to the higher dimensional space. This one required these parameters, gamma and C. Just use the default. Okay. And that's it. So you implement the algorithm, you train it on X train, Y train, you have an SVM, and then you predict on X test. I'm not going to convert to PCA. Here, I was just plotting these. Skip that, but I do want the metrics. All right, so let's go ahead and try this. All right, so that worked. And, oh yeah. All right, let me get SVM. Okay, so, oh yeah. Change that. What do you guys think? So 95%. It did not beat the neural network, right? So far the neural network seems to be the best. But yeah, this is another algorithm. And I've given you a little bit of the context and the story with support vector machines. You know, a lot of these algorithms have their own history and story, if you will. All right, let's take a look and see what else we have. So we've done support vector machines. So now you know how to do that multi-layer perceptron. We've done KNN, I believe. Decision trees, KNN. All right, we have also, where are they? Just so we covered SVMs, right? Random forest is like trees, but I'd be curious to see if it performs even better. Although that decision tree, what's it? No, the multi-layer perceptron did really well. So the one to beat currently is still the multi-layer perceptron, right? So that's the one still to beat. If my money right now would be on the random forest as better one. So let's take a look. So here's the random forest. Let's try it out. Okay, so same idea. Ensemble, SKLEARN ensemble. Whenever you see the word ensemble, sometimes it means it's like multiple algorithms are being used. So here is using several decision trees, essentially. From ensemble, import random forest classifier. Here you just use the default values for this one. You train it on X train, Y train, and then you predict on X test. Okay. All right, and yeah, let's just print the metrics for now. Okay, so that is loaded. You can see the workflow is pretty easy at this point. I'm sure you guys have memorized it. And now let's just run it. Let's see how well this one performs. Actually, not so good, right? So 94. So still the multi-layer perceptron seems, with 2 hidden layers, seems to be the best. Okay. Notice that you have more capability now because you can add more layers and so on. So that's good. Let's see. So I think we have one more left to try, and that's going to be here. Oh, the logistic regression. So let's take a look at that one. Logistic regression. That's one that we will do from scratch, actually. It's a very important one. Okay. So let's grab logistic regression. Okay. Same thing. Let's take a look. We have X train, Y train, X test, Y test. SKLEARN, see, dot linear model. You see this, right? Linear model. So neural networks are defined as non-linear models. And this is a big classification in machine learning, linear versus non-linear. We'll come back to this for sure after the exam, but it's one of the foundations of machine learning that we have to understand. So this comes from linear models, logistic regression. So we instantiate a logistic regression algorithm called LR. We're going to fit it once again, or our X train, Y train. We could predict on one sample. It's fine. And then just comment these two points out. And then we do want to predict and then evaluate the performance. We can comment out these three. I don't need that right now. All right, so let's take a look. All right, so green check mark. Now let's run the data, the train and test on this algorithm, logistic regression. Okay. Oh yeah, same issue. I haven't standardized the data, so right now I'm just using sure where that happened, but okay. All right, so I removed that one line, just get rid of that. All right, so we're performing the same thing. If you notice, this one got actually really, really good, right? 97%. So this is a logistic, purely linear, and it worked well. Almost as good as the neural network, but still the neural network seems to be the best, right? At 98.3%. Now, why did I want to do the logistic regression right after the support vector machines one? Well, because they're actually pretty similar. So that tells you how easy Iris is as a data set. I'll give you a homework assignment where you guys will do this, and I suggest you take a harder data set, right, for that. So essentially here, we're doing Iris data. So we got logistic regression, and we got SVM, support vector machines. They are essentially both similar, except that logistic regression is way simpler than support vector machines. Okay? So logistic regression literally, has the data, right? And what it's trying to create is a line that separates it in a two-dimensional space. In a three-dimensional, it's a plane. In a higher dimensional space is a hyperplane. All right, but essentially it does this. SVM literally does the exact same thing, but not on the original data. That's the key thing. So SVM, let's imagine, going back to the example, in the original space, it was like this, right? But it does this projection to a higher dimensional space. Let's imagine three-dimensional, right? So it projects up, and now the data is, in fact, linearly, this is called linearly separable. Do you guys understand? So that's essentially what's happening here. The SVM has this extra capability of doing projection to a higher dimensional space, right? PCA SVD compresses to smaller. SVM with something called the kernel trick projects up. How fun is that, right? So very interesting. So, but at the end of the day, they solve a line that separates the data, which is pretty simple, instead of having to do with a neural network figuring out that curve that separates both of them, which was considered really hard back then, okay? So now I ask you this question. Let's say that I gave you like this problem on the exam. And I tell you that for Iris, actually, this achieved 98% accuracy. And this one, let's say, or F1 measure, and this one is 99, something like that. What would you conclude about the data? Is the data easy to separate or hard to separate? Without, what would be your conclusion? Or I should put it in better terms, like, is the data linearly separable? That would be the question, right? So, well, by looking at these metrics, what would you say? Is it linearly separable or no? Is it linearly separable or no? It is. Why? Because this one achieve a high score, right? Yeah, exactly. Exactly. So if the data was like this, right? Do you guys see that? If the data was like this, what would happen really? Let's say that the original data is this, right? So then, oops, logistic regression, all it can do is create a line. So I have this. This is the famous XOR problem, right? So, but logistic regression at best would probably do, I don't even know where it would draw the line, but it's trying to minimize the error, right? So you would get probably the most coverage possibly by doing maybe that. Do you guys see that? So it's trying to find a line that minimizes error. So this might be the scenario where you have the smallest amount of error. You're going to have misclassifications because, okay, the X's are correctly classified. Do you agree? They're on this side. And the circles here are correctly classified. But what about all these circles here? They've been misclassified, correct? Because we have, by creating this line, we're saying that this is circles and this is X's. Okay, excellent. I get all these circles, correct. I get all the X's, correct. But these circles, guess what? They're misclassified. Got it, guys? So that's what logistic regression can do. Support vector machines can take the data, and obviously, you would need a neural network or something to build that circle, because this machine can only build, simple things, lines, planes, etc. And that mathematically is a lot easier than anything else. But support vector machines has like an ace up its sleeve, which is that it can take this data like this, project it to higher dimensional. Remember, this was R2, and in this example, I'm projecting it higher to R3, and I have this extra dimension, which now allowed me to like grab the inner, this was called the donut example, right? The inner part of the donut, I grab it out, I should have, but anyway, and it separates it like that. Any questions on this idea, guys? So you've seen, the differences, and actually, in this case, logistic regression performed really well statistically, which means the data is linearly separable. You didn't need to use a support vector machine, algorithm, or a neural network. But if you have a data like this one that's much more complicated, the expectation here would be that the performance would be, let's say, 78%, something like that, right? That's for the, but support vector machine, because of those tricks, would go higher. The neural network would go higher, and so on. Any questions? So you can see a lot of this is very much geometric in this way, and so on. All right, so let's take a look at where we are. Go back here. Okay. Yeah, so we covered all the algorithms, I think. So this was the script. We looked at the libraries, X and Y. Now notice, for the homework, I'm not going to do this part because at this point, you guys should be able to do these things. But just you can look at my scripts. There's going to be little code examples there to be able to solve the problem, and that the problem is pretty straightforward. I'll create the link in a second. Yeah, so I'm just looking here. I have several functions in here, but here's a PCA one. But we'll cover PCA later, so I'll skip that for now, because I want to cover PCA in another context. But we've done KNN, logistic regression, random forest, SVM, we talked about it. I'll skip the perceptron for now, because it's like from the 1940s. We did the multi-layer perceptron, decision trees. And then we've done scaling already. Yeah, that's good. All right, so that's the coding part for today. I'm going to create the assignment now. All right, and just let me know if you have questions. But it should be an easy homework. All right, so let's go back to, were there any questions about the code? Something you guys didn't understand about SKLEARN or anything like that? All right, good. All right, so let's go back to the table of contents. As you can see, this is the module. Create the assignment here. Let's call this one SKLEARN ML model. Okay, so this is going to be due a week from today, the 11th, 10 p.m. It's open now. Stay open until the 15th. Okay, so find a data set for classification and try to use something that is somewhat big, such as, let's say, at least 4,000 samples by, say, 40 features. Does that make sense? So I want you guys to start to use slightly bigger data sets. SKLearn has more power now, a little bit more power, so you can try bigger data sets. So this is important. But yeah, find a data set for classification. So remember, a lot of these examples were the iris data set, right? So you may need to remember, clean your data, change the labels to numbers, all that, it's on you. Find a data set for classification. Try to use something that is somewhat big, such as 4,000 by 40 or larger. And then using this data set and SKLearn, perform a complete machine learning pipeline using with at least 3, let's say 4 ML models. Okay, so use random forest, support vector machines, multi-layer perceptron. For each model, print the performance metrics and summarize your results and conclusions. Like that. Is this clear enough, guys, as to what you have to do? Right, so find one data set. Let me be more specific. One data set. That's all I'm asking for classification. Same places, right? Kaggle, UCI, same thing that you did before. Try to use something that is somewhat big, such as 4,000 by 40 or larger, using this data set and SKLearn. Described in class. Okay, so using this data set and SKLearn, perform a complete machine learning pipeline with at least 4 ML models. For each model, print the performance metrics and summarize your results and conclusions. Yeah. Any questions on what you need to do for this homework? And then, of course, submit a report. Submit a report with screenshots. I'll say a PDF. Submit a PDF report with screenshots and comments. Clear, guys? All right, so should be easy, right? So take advantage of these assignments because these are easy compared to upcoming ones. So let's go ahead. So click save and close. All right. Any questions? All right, so now I'll do a little bit of a lecture. Just there's one topic that I kind of want to introduce, and we have time today, and which is we talked about these performance metrics, precision, recall, F measure, and so on. So I'm going to talk about them. Okay, I'm gonna end this video here because